Picture, if you will, a source of energy, so radiant that it holds the key to our energy future. The sun, a source of limitless potential, emits almost 4 octillion watts of energy every second. That's a 10 with 26 zeros behind it. If we could harness just a fraction of this power, it would be enough to meet the world's energy needs many times over. In emerging markets like Vietnam, Malaysia, and Kenya, the race to capture the sun's energy is on. These nations recognize the transformative potential of solar power, not only for their economies, but also for the health of our planet. Vietnam aims to generate 20% of its electricity from renewable sources by 2030, while Malaysia has set a target of 20% by 2025. In Kenya, the Garissa Solar Power Plant, the largest in East Africa, is already providing clean energy to thousands of homes. But the path to a solar-powered future is not without its challenges. Efficiency in converting solar energy to electricity remains a hurdle, with current technology capturing only a portion of the sun's potential. However, advancements in material science and energy storage hold the promise of a brighter tomorrow, as well as embedded control technologies, including integrated circuits. Imagine a world where smart energy grids, powered by the sun, provide clean, affordable electricity to every corner of the globe. A world where the very source of life on Earth also sustains our modern way of living. How could Microchip technology help us further embrace the boundless potential of solar power?
Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience.
Our guest today is Jay Nagel. Jay is Principal Product Marketing Engineer at Microchip Technology, working out of the DS-PIC Digital Signal Controller Business Unit. He joins us today from our global headquarters in Chandler, Arizona. Welcome, Jay. Thank you for joining us on Beyond the Microchip. In the intro, we briefly talked about the increase in renewable energy demand and harvesting in emerging markets and the need to manage it efficiently through system monitoring, conversion, and other technologies. Tell us about it.
Thanks, Dana. First of all, thank you for having me on the podcast today. As you noted in the opening, I mean, there's challenges to a solar-powered future. There's a lot of challenges, and some of those challenges, one of the main ones is being able to harvest the maximum amount of energy from the solar panels in the array. So, I mean, during the day, these panels are subject to varying amounts of what's called sunlight irradiance, right? And really that's just a fancy term for saying what is the power per unit area received from the sun in the form of electromagnetic radiation, right? So basically it just measures how much energy is actually, or how much power is being captured per unit area from the sun hitting the solar panel. A lot of that is affected, the amount that you're going to get, it's affected by shading, any type of obstructions, inclement weather, even hot and cold temperatures, humidity, and various other environmental conditions. So that in itself, provides a potential barrier to being able to harvest the maximum amount of power from a solar panel array, or even an individual solar panel. And then once that power is actually captured, the system needs to transfer as much energy as possible that's captured to the consumer population, right? So that power has to be transferred to the consumers that use it, but then there's always going to be losses in that system. There's, not all of that power that's generated is going to get to, the consumers that are using them. Also, challenges involve system reliability and maintenance. Making sure that the solar panels are generating the maximum amount of power and they're operating to their maximum capacity. And then safety and security. That's a concern because you may have hackers, terrorists, those that want to create trouble. They can actually shut down the grid. They can actually penetrate the system, shut down the grid. Millions of people are gonna lose power. You're gonna lose power for critical systems. So safety and security is definitely a concern. You want to minimize how much space your energy storage systems are taking up. You want to minimize the amount of space that your inverters are taking up. because the more you're able to minimize the dimensional footprint of those particular systems, the more solar panel arrays that you can fit in a defined boundary or area, and the more energy that you're going to be able to create from that.
Harness and to convert. Right?
Exactly.
So what would you say is the importance of renewable energy, not only for the environment, for developing a robust scaling economy?
So a robust scaling economy with a rising population requires more energy resources to be able to support that growth. And if you only are using traditional fossil fuel sources to create this additional energy source, a byproduct essentially of that economic development is increased greenhouse gas emissions.
Mm-hmm.
If you're pursuing economic growth at the expense of, putting more or emitting more harmful greenhouse gases into the environment, you're actually defeating the purpose of sustainability. You're just achieving the growth.
You're trading one vice for another.
Exactly. And so this is, again, where smart grids come into the picture, right? And they can be constructed so that they can use renewable energy sources to provide additional energy sources to support the economic development initiatives. And they can be integrated into existing fossil fuel-based power grids.
Right, but this is not without its downsides or pitfalls, right?
Sure. One of the downsides of renewable energy source, or having any type of renewable energy source, is that there's situations where the energy that is sourced from the existing power grid and that produced by the solar panels, they need to be balanced, right? So a scenario that commonly occurs is that energy that's produced from, say, rooftop solar panels and solar farms is actually consumed more than the grid supplied energy during the peak sun hours.
Mm-hmm.
And by doing that, you're lowering the energy demand from the grid. And so what this results in is that you have increased strain on the grid while it attempts to process the resulting extreme fluctuation on supply and demand of that energy as the sun reaches its apex during the day. And then once it sets, you get high demand from the grid.
You get a spike. Yeah.
You get a spike from the grid. And so what that can cause is a blackout. It can totally cause a blackout. So
the sun's providing energy to your solar array, and because of that, you're doing less of a draw on the grid. So the grid doesn't know how much energy to generate, right? Because you're taking less and less. And then by the end of the day, when the sun goes away, as it does every day, you're talking about that's when there's a strain on the grid because that balance is kind of off.
Exactly.
Okay.
Exactly. And so if you have an effective energy monitoring system that can monitor the overall energy demand and then adjust what the primary energy source will be in a smart grid type of configuration and be able to balance the energy delivered to the community or ecosystem, that can bring efficiency to the entire power grid structure.
So does the monitoring system act as a warning to the grid?
Absolutely.
Okay. So then the grid knows what to expect.
Exactly.
Okay.
Exactly.
All right. Then let's talk about solar power monitoring systems. Obviously, we have this challenge of solar power is great. Solar power adds during the day when we actually have a sun, but then eventually at night the sun goes away and you have to bring your reliance back to the grid. So a monitoring system is that nice go-between to help balance, right? So how does the monitoring system work?
Really, the monitoring system can really help overcome some of the system design challenges that I was talking about earlier. So the basic function of the energy monitoring system really is to monitor the electrical assets in a solar plant. And when we talk about assets, we're talking about the inverters, we're talking energy storage units, and then any power distribution centers that distribute the power generated accordingly. And overall management for the smart grids to account and really help to resolve some of the potential pitfalls of implementing a renewable energy source into an existing power grid. So let's talk about smart grid management a little bit, because I think we have to back up,
okay.
Right? And so really what the smart grid does is it provides that two-way communication between an energy consumer, such as residential, plant, whatever it may be, and then the power grid. which is the energy producer, it makes the energy usage more efficient and the delivery of that energy more efficient and reliable to either that residential home or business.
Mhm.
And so the way that it does that is that it incorporates sensing, any type of wireless communication, automation, and really cloud-based information tools to make the grid more efficient and reliable. And so high efficiency and reliability in the integrated circuits that comprise that smart grid actually make the grid more efficient and reliable. It enables the smart grid to deploy its function. And the smart grid allows the integration of renewable energy sources such as solar, wind, and hydro into an existing fossil fuel-based power infrastructure.
These aren't just ideas, right? We're actually deploying this somewhere now. We talked about emerging markets in the opening.
Mhm.
Are there any specific examples you can think of where we're using this now?
Yeah, I mean, in reference to the mention of Vietnam and Malaysia in the introduction, a lot of investment in renewable energies in those countries have originated from the ASEAN Power Grid Initiative.
That's the Association of Southeast Asian Nations.
Correct. Yes. And so far, what that initiative has accomplished is the installation of 310 gigawatts of total power capacity that's originating from both fossil fuel and renewable sources. And by the end of 2022, 30.4 gigawatts of new capacity was added. And the share of the energy contribution from wind and solar constituted about 10% of the total energy capacity in calendar year 2022, with an expected share increase in renewable sources to about 38.5% by 2025. So there's there's going to be a huge increase in share growth there. But the problem is that even though, for instance, even though solar and wind energy sources increased their installed capacity by 29 gigawatts in that decade between 2012 and 2022, the contribution to that total electricity generation was only 2.4%. This is an opportunity to introduce an energy monitoring type of solution to be able to increase the share of electricity generation from renewable sources. And Microchip has had a very, very big impact on that with our solutions.
So talk specifically about emerging markets. I know that the ASEAN power grid is kind of connected. I mean, I've seen diagrams of power that's done up in the northern section up by Laos, and it kind of comes all the way down through Singapore. And it's supposed to, at some point, connect with Indonesia and the Philippines, right? Is the idea that the smart grid management could apply to that entire grid?
Absolutely. Absolutely. I mean, one of the big initiatives is the quote unquote sharing of electricity amongst all the regions,
right,
so that all these regions can prosper and grow together. To be able to manage the sharing of that energy, the smart grid implementation with an effective energy monitoring solution will be really key to being able to execute those goals and objectives that they have.
The idea was to share surplus energy in one area with an area that has higher demand from the things that you were talking about earlier: shade, obstruction, humidity, temperature fluctuations like hot and cold. That's all designed for the smart grid to be able to keep that balance going, not just between the grid and the solar array, but between all the member states inside that grid infrastructure.
Correct.
Does that sound right?
Correct. Absolutely.
Okay. What devices are we talking about? What would apply to this type of application?
So in general, any energy monitoring system requires the need for a microcontroller that has real-time control capabilities. One example being the DSPIC digital signal controller that's offered by Microchip.
Mm-hmm.
One of the necessary features of that microcontroller with real-time control capabilities is that it can sense and react with minimal delay to changes in information that's acquired from sensors in the system to dynamically adjust the system performance to continue harvesting the maximum amount of power, like you were just talking about.
Mm-hmm.
So one example of that dynamic adjustment is changing the angle of the solar panel array to be able to capture more power from the sun if there happens to be some kind of obstruction, whether it's temporary or permanent. There's motorized control of the solar panel array to be able to adjust the angle at which the solar panel is positioned so that it can capture more energy.
Mm-hmm.
Another example is deciding when to transition to energy usage from an energy storage system instead of actually pulling from the power grid. Some other examples of devices in Microchip's portfolio that can support this kind of operation are discrete power management integrated circuits. They provide that stable voltage source to be able to operate the electronics in the controller with a minimal consumption of power. In inverters and energy storage systems comprising that renewable energy system in a smart grid, wide bandgap semiconductors such as silicon carbide provide that high power density device capable of operating at very high power levels with minimized footprints for cost savings. Also included in the solutions that Microchip is working on for energy monitoring systems are Ethernet controllers. They provide that medium for reliable, fast, and robust transmission of data between other subsystems within the smart grid, so that the information exchange can make for more seamless operation of the entire system.
It's kind of that total system solution concept that we're talking about, right? That we have
Exactly.
multiple products across multiple areas that we can bring together for one convenient, for lack of a better word, a bundle. The idea is that each of these components has a specific job to do that all contribute to the success of the whole.
Exactly. They all work in concert to be able to implement a control system that regulates the operation of the smart grid.
And because we're talking about something as important as critical infrastructure, I'm going to assume that there were some evaluations based on specific metrics.
Absolutely. One of the things that set Microchip's solution to the top of the list was its compliance to international standards. So all these smart grids have standards, compliance standards that they need to adhere to. One of those standards involves electricity metering equipment. There are specific IEC standards that the digital signal controller was able to adhere to in its operation, specifically in terms of accuracy and resolution of voltage and current measurements. That definitely made it a prominent decision choice with the customer. And then some of the things that were included in the digital signal controller was the ability to have flexible communication interfaces. In this particular instance, the protocol that was required was the SPI protocol, the Serial Peripheral Interface Protocol, to be able to communicate with other devices within the system. And then a high level of integration. A lot of the components per se, that were needed to be able to measure voltage and current, for instance, are actually integrated within the microcontroller itself, making it a very cost-friendly type of proposal, right? So that goes back into being able to minimize the footprint of the entire system. But not only are you minimizing the footprint of the entire system, you're also minimizing the cost and the weight as well. And one of the great things about Microchip's solution offering, especially in the sustainability space as a whole, is this ecosystem of software development tools. We've got software development tools that will help you to automatically generate software code for your system, and then full-blown, ready, off-the-shelf reference designs that can be available at your fingertips to be able to create your sustainable system. And so one of the examples that I want to give of this, something that's really great reference design that Microchip is coming out with, is this 400-watt solar charger. And this is a really, really great off-the-shelf system to use because it's actually going to charge using a solar panel as an input, the solar panel output as an input into the system. It's actually going to route current to charge a battery, to charge a lithium-ion battery. And then that lithium-ion battery is going to power streetlights, and it's going to power consumer devices. It can power, any type of camping equipment that a user might have, and it'll be quite portable once it's packaged into a system. So this is a really great off-the-shelf design to create essentially a system to be able to power some of those things.
And as I think about the metrics that you described with IEC standards, resolution, communication protocols, there's a lot of adaptability and there's a lot of flexibility built into the system. That's probably pretty important for areas where population fluctuates and standard of living is rising, probably at an uneven pace. There are certain markets that are growing much faster with a much higher standard of living, which means their energy requirements are also going to increase. So that flexibility is nice to have, right?
Absolutely. Systems like these are always collecting data on the environment. They're collecting data on how much energy is produced, how much energy is consumed at different times during the year, in different seasons. It gauges how much power needs to be delivered to the community based off of what the community needs. So that real-time sensing of the system is able to detect situations where there's more power demanded and hence can dynamically adjust the system to be able to deliver that power if it can, or it will trigger some data-driven sources to let the community planners know maybe more solar panels are needed to be added to the existing structure.
Right, so it allows for demand and supply adjustments.
Correct.
One thing that you and I were discussing off mic is that this isn't just an idea that we're looking to push out into the market. We're actually practicing what we preach here. We have a solar facility of our own in Thailand. Is that correct?
Yeah. In addition to Microchip's technology solutions, what you just mentioned is a great example of our contribution to environmental sustainability through our operations. What's really, really neat about this facility and notable is that it's a floating solar farm that's located at our Microchip Thailand facility, which provides for about 16% of that facility's total power consumption. So it's our solutions and it's our operations. It's like a twofold. Customers can read about this in our ESG report.
Yeah, our sustainability report. It's nice to see that we believe in it enough to use it ourselves. We don't often see that from many corporations. They'll usually push a solution out that they don't necessarily believe in. So that's a very nice thing to have. So Jay, suppose one of our listeners has a use case for this technology. How could they adopt it?
So for residential and commercial implementations, independently licensed contractors can install solar panels on rooftops, complete with inverters that convert the power from the solar panel to operate the appliances and gadgets that are in your home, along with energy storage systems to store electricity during peak sun hours, and then use that energy during the nighttime when the sun sets to save consumers money on their bill. So this energy can also be used to charge an electric vehicle, and it can also transfer energy back to the grid. And so energy monitoring systems, they can be used to really report energy usage to any centralized based server and report that information on either a PC or a phone app. And this allows the consumer that flexibility to enhance the energy usage from the solar system that they've implemented, or they can report problems and technical malfunctions that are occurring on the solar array panel. Now, I actually had the good fortune of having a close friend of ours implement solar in her home here in Chandler, and I was able to really listen to her experience in implementing solar in her home. And she was a really interesting subject to talk to because she herself is not a power engineer. She's not an electrical engineer. She's a brilliant person. She's a scientist, so she likes to delve into the details and look at data.
She probably wants a lower power bill.
And she probably wants a lower power bill. You must have great clairvoyance because that was her primary goal. But she didn't initially consider solar. But it happened to be that during the pandemic, a lot of people had extra time, which is kind of an interesting thought. When you've got more time on your hands and the world kind of slows down, you have the time to think about things that you normally wouldn't even consider. And so in this particular case for her, it was solar. So she had time to dive into the details. She called our local energy utility company here in Arizona. And she procured multiple quotations from different contractors. So the great thing is that there's a lot of contractors out there, a lot of licensed contractors that are available to install solar in your home. She selected a contractor that really helped her to understand what she needed in her system, right? Based off of her energy usage, based off of her living habits, so to speak, and based off her lifestyle, essentially.
Right.
I mean, she did a lot of research to really understand for herself what those energy usage needs were and what was her exact energy demand curve. And so, one of the things that really attracted her to the solar was being able to have an energy storage system. Now, this was key, right? The energy storage system enabled her to store large amounts of energy during off-peak hours, which happens to be, when the sun is the most prominent in the sky. Right. According to the kind of laws, rules, and regulations of the billing plans, right, that are provided by the utility company. And then she was able to kick on her energy storage system during peak hours to be able to use that energy. And then whatever excess was being produced, she was able to transfer that and sell that back to the grid.
Yeah, that was my next question is, what did she do with the excess?
Yeah. But one of the things that it's great to have excess energy, right? Because it kind of tells you that, I'm using this energy really effectively, right? And I'm not using a lot. So I'm actually doing something good by giving it back to the grid. But one of the things that kind of, frustrates her is that she wishes that she had a much faster payback for her investment in the solar system. And hence, she wishes that she could sell the energy produced from the panel at a higher price point.
Market rates.
Yeah, exactly. So she was hoping that that she can sell at a much higher price so that she can get to that break-even point much sooner and really justify her investment in solar. But essentially, if you don't do that, right, if you don't get to that break-even point much faster, you're essentially paying for all your energy usage up front by putting a solar system in, which is counterproductive to the goal. So the energy monitoring system and the enhancements of being able to store more energy and use it strategically is going to impact not only having a lower bill, but getting to that break-even point much faster.
It also helps with scale, right? So if you're generating excess energy at those peak times, you have the ability to feed energy back into the grid, and the grid can now go somewhere else where maybe there isn't power, and that would allow the grid to scale, would it not?
Absolutely. And with the flexible and, just to add to your point, with the flexible and modular energy storage system, if your energy needs in the home change, let's say, for instance, there's a change in your lifestyle where you're consuming more energy, you can actually add battery cells to your energy storage system to be able to account for that.
Right, and then that would allow you to become a little bit more independent from the grid such that balance maintains, right?
Exactly.
Do you have any predictions for the future of solar energy monitoring systems or how the technology could enhance the human experience, like the examples we talked about today?
One of the things that I didn't highlight or talk about was or in great detail was artificial intelligence, machine learning
AI.
capability.
Yeah, get into that.
Exactly. So, as I had mentioned before, with the microcontroller-based system, you'll be easily able to collect data, build historical data on voltage and current outputs for various sections of the panel. And with that, the monitoring system is able to predict with some level of certainty the expected power delivery for specific days and time periods and seasons and stuff like that. So in addition, the use of that historical data can also be used in a way to detect faults that are in the system. If the quote unquote expected output is not achieved on a particular day or time, which can drive maintenance actions.
Right.
So if for the last 5 years, if you've been getting this many kilowatt hours of consumption and generation, essentially, and all of a sudden you're not seeing that anymore, system can flag and say, oh yeah, this section of the solar panel array is not producing the expected output.
So AI would allow for that demand and supply preventive action?
Correct. Correct. And it can bring overall balance over a longer period of time to energy produced and energy consumed using the different renewable sources and the existing fossil fuel based infrastructure that's on the power grid.
Right, and we hope that increases efficiency and lowers cost over time.
Correct.
Because we all want to lower power.
Absolutely.
Any final thoughts, Jay?
Earlier in the discussion, we highlighted a few key technologies that comprise renewable smart grid systems. Some other areas where we can complete the solution are the 8 and 32-bit MCU and FPGA devices. Also, some areas that we can fill in the solution is with our signal conditioning and analog measurement discretes. So some examples being analog to digital converters that can take a reading from a sensor, which is usually a voltage measurement or current measurement, and then it digitizes that signal so that the microcontroller or microprocessor can act on it if necessary to adjust the system's performance. Also, you've got devices such as operational amplifiers that can be used in active filtering circuits to condition a signal so that it can be properly read by the microcontroller. Also got integrated multi-die products. And then one key technology that I think we can't overlook is our temperature sensors. We've had a lot of success implementing temperature sensors. And so it's very important to know what the temperature of a solar panel is. Because if the temperature is too high, as the temperature actually increases, it reduces the amount of energy that a panel produces. So using temperature sensors at critical points within the smart grid, especially on solar panels, is definitely a value add to be able to harvest the maximum amount of energy. Mm-hmm. And then our IoT and 5G solutions not only allow data to be uploaded into the grid, but you can actually extract data wirelessly to like cell phone or to any cloud-based type of system to be able to report out on system status.
Yeah, that's one great strength of Microchip is that it has all of these various different types of components. Also, I think we're the only firm that does development of 8, 16, 32, and 64-bit microcontroller solutions. There's just so many things in the product catalog. It's really good to see that we're applying all of these things to these different applications that apply to our megatrends like this.
It's great. I mean, the user can essentially build their own system.
Jay, this was great. Thank you very much for joining us.
Thank you for having me.
Jay Nagel is a principal marketing engineer at Microchip Technology. He specializes in DSPIC, digital signal processing technology. He joins us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.
Honestly, I didn't hear about floating solar panels until this Microchip Thailand thing. I never knew we did that.